Alright, we're in chapter 13 still. We're in the second video now. And we're going to we just looked at vapor pressure, and we looked at vapor pressure diagrams. Now we're going to be looking at surface tension and some other topics. So we'll start with surface tension. And I'll start out by asking you, have you ever noticed if you spill a cup of water on certain surfaces, maybe around your house, sometimes that water will bead up and kind of make like a droplet or a sphere? Or maybe you've seen a video of someone in the past, because they don't allow us to do it anymore, but maybe someone playing with liquid mercury. And the mercury droplets are like little spheres that form on the surface of like a desk or a countertop. And instead of the liquid, which liquids are supposed to flow, right? And the molecules or the particles of a liquid are supposed to kind of slip and slide around, and they don't contain a certain shape. They're supposed to take on the shape of the container. So it would make you think that if a liquid spilled onto a countertop surface, why are the particles beating up? Why are they not spreading out and just kind of flowing across the surface? Well, it has something to do with this topic of surface tension. Surface tension is the resistance of a liquid to increase its surface area. So it's the resistance of a liquid from spreading out onto a surface that it's been poured onto. And sometimes liquids will exhibit surface tension. The molecules on a liquid surface, we know, are strongly attracted to molecules inside of the liquid. And what happens is surface tension will increase if you increase the interactions or the attractive forces, the intermolecular forces between the particles. So some compounds with higher intermolecular forces exhibit a lot of surface tension properties, and other substances with less intermolecular forces of attraction between the particles won't exhibit as much surface tension or form these droplets or spheres. So what in the world is going on? Well, let's look at this diagram here. The first thing I'll say is the layer on the surface of a liquid is produced by uneven intermolecular forces at its surface. What do I mean by that? The molecules at the interior of a liquid have equal intermolecular forces in all directions. But the molecules of the liquid that are at the gas-liquid interface, the surface of the liquid, will always experience a greater attraction toward the center of the liquid than toward the gas above it. So what's going to happen is there's going to be a preferential pull of molecules at the surface toward the inside of the liquid. So molecules on the surface of the liquid, those on the outside that you see, will be pulled inward more strongly than the ones on the inside. And this is what's going to create a thin, like elastic skin layer that creates the surface of that liquid. And I'm going to try to draw a picture to show you what's going on here. So I'm going to take a little invisible microscope that doesn't exist, and let's say that you have, I don't know, this beaker here, and let's say it's closed for whatever reason, and that beaker has a liquid in it. What I'm going to do is I'm going to take my little molecular goggles, and I'm going to take a piece out, and I'm going to inspect it from the side of this flask. Alright, so I've got my little molecular goggles here. I've got the surface of the liquid here, so everything down here is liquid, and this is the gas phase above the liquid, the head space, I'll say. So here, right here, this is called the surface of the liquid, where we will notice the tension occurring. What I'm going to do is I'm going to draw some different molecules in this liquid right here. Alright, so I'm going to draw a molecule on the inside. This would be the interior particles of the liquid that I was referring to. What we're going to discover is that those interior liquid particles have equal intermolecular forces in all directions, so no net pull in one direction. I'm also going to look at two other particles. I'm going to look at a particle on the surface here, in the middle, kind of the liquid, kind of like over here versus inside here. And then I'm going to look at one on the corner. I'm going to see what happens here. Alright, so let's see here. Let's look at the molecule here on the surface. So what I'm going to do is I'm going to take some of this liquid out. So I'm going to get like a little pipette, and I'm going to suck some of this liquid out, and I'm going to, so let's pipette it up. I'm going to suck it up in my pipette, and I'm going to take this liquid, I'm going to put it down on the desk, and it should spread out, right? It won't spread out. Here's the desk, and something interesting is going to happen here. All right. The particles that are on the interior of the liquid, represented by this one, those particles are surrounded by particles, I'm going to make them in yellow so they don't get in your way, in all directions. So the particle on the interior of the liquid is in close contact with several other particles inside the liquid. What this means is that particle has intermolecular forces with this particle, 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 and with that particle. And the intermolecular forces that exist between all the particles of liquid are equal. So what I mean here is that here's your particle again. If it's getting pulled or has a force of attraction toward the particle maybe above it, because it's in the liquid phase, it's in close contact with several particles in all directions, it will have equal pull in the opposite direction. So the net pull isn't that the particle will be pulled up or down. The net pull is that there's no pull. Overall, that particle is moving randomly, not in one net direction. And this occurs all around that particle. So overall, that particle does not have pull in any one direction. Alright, let me erase everything I drew here in yellow. So that particle just remains. Now, what about the particle on the surface, though? That particle on the surface is not surrounded by particles in all directions, because there's no particles that exist in the headspace above that liquid. So it's only in the lower hemisphere, we'll say, that the particles are interacting in the liquid phase. There's nothing in close contact above it. So that particle on the surface is pulled to the left, and it's pulled to the right. It's pulled to the left and the right equally because they're equal opposite pulls. However, when we go down to that particle, so here's your particle again, there's a particle right below it, pulling or attracting that particle down toward it. But because it's on the surface of the liquid, there's no particle above it pulling it up. So the net direction, north or south, is that the particle gets pulled down south, or down into the interior center of the liquid by the particle surrounding it only on one side. The same thing is going to occur here and here. The net pull of the particle in the center of the surface of the liquid will be pulled, here's the center of the liquid, this particle will be pulled down toward the center of the liquid. What about this particle over here on the side? The particle that's over here on the side only has 1/4 of its three-dimensional space being occupied by other molecules, meaning there are particles to the left and down, but there's nothing up here, there's nothing to the right, and there's nothing to the right down below it. So what is the net pull going to be? Well, this particle here is pulled left, but it's not pulled right. It's pulled down, but it's not pulled up. So if your net pull is to the left and pulled down, then it's going to be to the left and down, once again toward the center of the liquid. So the net pull of the particle on the side of the liquid sample, once again, like we said earlier, the molecules at the surface will be pulled with greater attraction toward the center of the liquid because the net pull is in that direction. So if I even have, let's say, a liquid over here, that'll be pulled this way. So it turns out when you're at the surface, and I'm just going to do a general surface. Now let's say that we've poured this liquid onto the table. Alright? So we poured this liquid onto the table. You would expect a liquid maybe, initially when I told you it flowed, to kind of just spread out in all directions, slip, slide, and move around. But what happens is, because of intermolecular forces, the particles at the surface are all pulled more tightly due to intermolecular forces of attraction with the surrounding particles toward the inside of the liquid. And when that happens, think about taking a big parachute and think about pulling all the particles like you have tons of strings and you pull them all in toward the center real quick, right? That's exactly what happens. These molecules are all on the surface getting crowded and pulling in toward the center. And what you end up creating is, instead of spreading out like here, you end up creating, so we're on the surface here, a bubble. And the surface particles, which are all tightly held together, kind of like a nice elastic moving skin, are all pulled tightly in toward the interior where most of the particles are, and there's higher intermolecular forces. So the particles end up making this big skin that pulls together like a droplet because they're all unequally interacting with particles around them and pulled toward the center by those unequal intermolecular forces. Alright, so that preferential pull of molecules onto the surface toward the interior of the liquid is what's called surface tension. Surface tension is directly related to the strength of the intermolecular forces between molecules. So if you have particles or molecules that have higher intermolecular forces, they're going to have a greater surface tension, which means they have a greater ability to bead up or to form droplets on a surface than liquids that would have lower intermolecular forces between them. It's a pretty cool phenomenon, actually. Also related to that phenomenon is something called capillary action. So what is capillary action? I'll tell you when I had my first experience with capillary action. I think I was about 8 or 9 years old probably, and I went to the doctor's office. And they took my finger, so I've got my little finger here. And there's my finger upside down because they took a sample of blood from me. I don't remember why, but they had to take a sample of blood, so they took a pin real quick, or, one of those pin pokers, the machines that do it for you really fast and hard so you don't feel anything, but you always feel something. So they poked my skin real quick, and a droplet of blood came out of my finger there. Aren't I a great artist here? But a droplet of blood came out, and it was just kind of sitting there, and it's like, oh, there's blood on my finger. And what they did was they took a small capillary tube. A capillary tube, by the way, is a tube that is very narrow. It's usually made of glass, and both ends of the tube are open. So it's like a really, really, really thin glass straw almost. Except this tube, you do not need to suck. So they took the tube and they collected my blood through the tube. All they did was put the tube up to my finger. Oopsies, that would be bad. Alright, they put the tube up to my finger, and they didn't have to suck or anything, but when the blood came in contact with the tube, it spontaneously rose up the tube, and the tube became filled with that blood sample. No sucking required. All the blood got into the tube. And it occurred on its own. There's my blood sample. It was done. And that was my first experience with capillary action. I'm like, how did that occur? And you've probably seen this in several other ways. Have you ever noticed that when you water plants, the plants get water all the way to the stems and the leaves, and you're watering the roots? The roots that make up the plants and the trees and everything, they suck up water naturally, or the water spontaneously rises through those root systems, those little narrow tubes, by a process called capillary action as well. So what in the world is capillary action? Well, that's the definition. It's the spontaneous rise of a liquid through a narrow tube. How does it occur spontaneously? How come we don't have to? What is the force pulling this liquid up into this tube? Well, it turns out there's actually two forces competing against one another in this process. The first force is something we've actually looked at before. We just didn't define it. It's called the force of cohesion. What in the world does that mean? Cohesion is the mutually attractive force that exists between like molecules of a particular liquid. These are the intermolecular forces of a liquid. The cohesive forces of a liquid are the intermolecular forces of the like molecules of that liquid that want to hold them together. This is the same force of cohesion that produced the phenomenon known as surface tension. So the like molecules pull one another together. They have a mutual attraction between them that exists. There's a second force, however, that's competing against cohesion, or the liquid molecules sticking together with themselves. The opposing force is called adhesion. Adhesion. You've probably heard of a similar form of this word before, adhesive, like sticky tape. What does it mean to adhese something? It means to take one type of material and to kind of stick it to another material, right? Like you wouldn't buy tape to stick it to itself, although I think people are doing that now. It's kind of a trend. But anyway, most of the time when you take tape, you're not sticking tape to tape. You're taking tape and sticking it to paper or a packing box. Your two unlike materials are going to be forced to be held together. So think of that when you think of this word adhesion, or the force of adhesion. Adhesion is the attractive force that exists between two unlike materials. All right? So instead of maybe the liquid particles attracted to each other, the force of adhesion would be the liquid particle interacting with the tube, which is a solid particle. So adhesion is the property that's responsible for capillary action. What's occurring is, if you have a tube, let's say it's made out of a certain material. I'm going to call the material S for solid. So it's made out of one type of particles on the walls of the glass tube, and you've got a liquid particle here that's kind of outside the tube, so it's an open tube. So the tube's made of solid particles. The liquid is obviously made out of particles in the liquid phase. These are two unlike materials. So the liquid is maybe water. The solid is maybe glass. So the liquid can either choose to only interact with itself and not climb up the tube. And this is the property when liquid interacts with itself. That property of that force of attraction is called the cohesive forces. They want to stick together with themselves and not intermingle with the solid. However, if the liquid comes in contact with a material that it really wants to interact with, maybe they have very similar intermolecular force types, like charge forces that bring them together, that liquid can choose or can interact with the second material. So we'll say A interacting with B. If that liquid particle chooses to interact with a particle not like itself, like the glass walls of the capillary tube, there's an intermolecular force of attraction occurring there as well. Well, it turns out that's called adhesion, by the way. When capillary action occurs, the adhesive forces are stronger than the cohesive forces between the different particles. Meaning, so adhesion wins. The force of attraction here between the liquid in the solid phase of the glass tube is a stronger force of attraction than the liquid to itself. So what happens is, drawn up by that force of attraction, intermolecular forces, the particles begin to interact with the solid phase, and the liquid particles begin to fill the tube. Alright, so they're climbing due to this force of attraction pulling them up. It turns out that these two competing forces are not always one is strong and the other is completely weak. Sometimes they are actually competing with one another. And we've talked about this word meniscus before in lab. We know that when we use something like a graduated cylinder, for instance, you go and put water in a graduated cylinder, it has a meniscus that's produced, right? It's not a complete line, but it climbs up the walls of the container as well. So it turns out that in this hollow tube, the shape of the meniscus in the capillary tube reflects the relative strengths of the cohesive forces versus the adhesive forces between the liquids. So what are these differences? The shape of meniscus is, if the adhesive forces, remember that's the solid of the capillary tube and the liquid interacting, if the adhesive forces are stronger than the cohesive forces, the liquid is said to wet the surface of the capillary tube, or to really adhere to it. What you're going to see is you're going to see an upward curved meniscus, which is called a concave. So in that capillary tube, if you see a concave meniscus, meaning curving up, instead of being linear, it means the adhesive forces are stronger, so the liquid wants to climb even further up the tube to further interact with as much solid surface as it can. It's known to wet that surface. However, if the cohesive forces, the liquid likes its particle forces better than it does the solid forces with the container, the liquid is said to be non-wetting inside of the container. Basically, the liquid will curve downward inside of the capillary tube, which means you'll have a convex meniscus. This is when we curve downward. Instead of being straight, there's less surface area hugging the tube than it wants, because once again, this is like a surface tension, a bubble building up, right? Because the material would rather interact with itself than interact with the capillary tube. An example of this is something like, have you ever used Rain-X on the windshield of your car? Rain-X is a substance that's used to de-wet the surface of your car, to bead water molecules up. It turns out that water really likes glass. For instance, remember when you are in the lab and you put water inside of the graduated cylinder, you always notice that concave meniscus, because water adheses to glass, or it likes the glass so much that it wets the surface. Well, when you're driving your car, this can be a problem, because if you just have untreated glass and it starts raining, the water, when it rains, will spread out and it will blur the vision of the driver as it wets the surface. So now we have treated glass on our windshields a lot more than often than not. But before the treated glasses, a lot of people used to use Rain-X as a solution on their car that changed the forces of attraction on the layer of that glass. If you put the kind of oily substance on it, it is a film on top of the glass that changes the intermolecular forces, and the water likes itself and does not like the intermolecular forces of the Rain-X, and it will bead up. So it will have these cohesive forces versus adhesive forces. It will bead up, and that doesn't blur your vision while you're driving. It just washes off the windshield, it strips off, those beads roll off as you drive. It's really nice. But that's an example of using these two different forces to solve a problem. So while water has stronger, or interacts with glass very readily and has very strong adhesive forces, so it will have concave meniscus in a capillary tube. Something like mercury, it turns out. Mercury beads up really well inside of a glass. If you've ever looked at a manometer, a barometer with mercury in it, you've noticed that you should see instead a convex meniscus, meaning that it's a non-wetting type of material. It does not like the glass. The cohesive forces are stronger than the adhesive forces.